we're still in Leiden, and I'm not, that was on my slide, I'm embracing so, okay. Yesterday, I talked about, maybe switch up the light for I introduced this orbital degrees of freedom, and the wave functions, why, especially 3D and 4F are so confined, why the nucleus is so localized, the electron interactions U and the functional J, you heard about it, coupling to the, or how this can give rise to MOT insulators, Hubbard models, and magnetism, and that then also came back to working from particles. So I will now become a bit more specialized and start looking only at orbital degrees of freedom and actually only at strong coupling. So the U bigger than the bandwidth. I'll first introduce this EG and T2G orbitals and now say how they're split. Compare a bit, say still hand wave and spin and orbital degrees of freedom, and then go a bit more formal orbital representations, orbital hopping, and how orbitals change the super exchange, how it changes the Hubbard model, which is actually the 1s orbitals, how does it change if I include 3D orbitals. I will not do 4F because it's just another type of complication that I don't want to get into. And then tomorrow still I will talk about compass model, and then the e.g. Google-Chomsky Hamiltonian, talk about some of its symmetries and degeneracies, and talk about order by disorder. Okay. Like yesterday, I'll just go on and see where I get. Please feel free to interrupt and ask questions during the talk. I'll just stop earlier and if I have any questions. So just to come back again, you have atom, you have sp and d orbitals, the Fermi level, somewhere, let's say, in the middle, and in 3Ds. In the solid, we get bands, so the 4p and the 2p here, they form bands, and also the 3D. And this actually, this kind of picture is the one you encountered when the pnictides were discussed, right? Like many orbitals, and the Fermi surface that forms here is made up out of many orbital components. The extra thing that I want to put on top actually is these correlations. So this limit that large U, bigger than T, bigger than say the bandwidth, which is not the case of not many people believe that is the case for iron pnictides, but it is the case for many other transition metal systems, especially oxides. And then I have the MOT insulator. So here I have this gap of maybe a few eV or so, a big energy gap, and this splits up to 3D levels. And now the question arises simply, I have some orbitals that appeared here. So you could say, I start with an atom with definite orbitals, I form bands, this orbital information is washed out, electron delocalized, but now I put on the on-site correlations, and now the orbital degrees of freedom reappear. There are orbital moments now there. Electrons occupy a specific local orbital. And now the question is, well, which orbital will be occupied and which one will be empty? So there's now some dynamics on the lower energy scale that starts to kick in, or can kick in, and determine which orbitals are in fact occupied. And which kind of orbital ordering forms. Okay, to discuss this, first I'll tell you how the EG and T2G manifolds are split, or in general, and also Tom mentioned this, the crystal field that kicks in lowering the symmetry of the atom to, for instance, cubic, they're splitting the orbital. So let's, just to be definite, let's take a perovskite crystal structure. This is a manganite, this is mean calcium manganite, perovskite structure. Well, you know what it is. It's in this case, Mn06 octahedra that have manganese in the middle, oxygen on the corners, and these corners between octahedra are shared. Corner connected Mn06 octahedra. important thing is the manganese is in the middle. And depending on doping, in this case, if you do just the electron count, the manganese is either 4 plus or 3 plus, depending on the calcium content. So how do the orbitals split here? Well, there's this cubic crystal field splitting, as Tom said, 10 dq, which splits the T2G orbitals, lowers the T2G with respect to the EG orbitals. Why? Well, it is because they are in the middle of this cube of oxygens, and these orbitals, EG orbitals, have electrons with lobes pointing towards the negatively charged oxygens. Yeah, also this x squared minus y squared, its lobes are towards these negatively charged oxygens. That means that the Coulomb repulsion between electrons in these EG orbitals and the negatively charged oxygens is large, and therefore these orbitals are pushed up in energy. Compared to the T2G orbitals, right? Well, you cannot see it very well in this picture, but these lobes are actually pointing in between oxygen, in a direction in between two oxygens. So these are, from the Coulomb point of view, lower in energy. But actually, this is a very simple explanation. In general, there's not only a Coulomb reason where these orbitals are split, but also there's covariance. Also the fact that electrons can form bonds, and if they are, the bond formation in general depends whether an electron is in a T2G orbital, because then it has a different symmetry, different overlap with the oxygen than when it's in the EG orbital. At any rate, the result of this is a rather large splitting of the T2G and EG. Also again, electron volt and energy scale, let's say. And now if I have manganese 4 plus, where if you do the electron count, you have 3 electrons in the 3D shell, you have to fill this, these states. So here are the 5-fold degenerate 3D levels, splitting up the T2G and the EG. I have to put 3 electrons, and I can put all 3 electrons now in the T2G shell. Hund's rule tells me all the electrons one has spin up. So this is a very simple situation. Actually, I have a filled shell of T2G, and that's it. Well, what happens now if I have manganese 3 plus? So I put an extra electron here, D4. Well, there are 2 possibilities in principle. Either the extra electron has spin up and goes in the EG shell. This is favored by the Hund's rule coupling, because now it has a spin here parallel to the 3 T2G spins down there. But of course it has paid, we have paid the energy 10 dq in this case. If 10 dq becomes very large, and the pictures also that Tom has showed, if 10 dq becomes very large, then it's more favorable for the electron to go in the T2G shell with spin down, paying the Hund's rule energy, but gaining or avoiding the crystal field splitting. So that's why, in general, let's say, this doesn't happen in the manganite. So the manganite situation is such that this high spin configuration is favored, but there are many systems. Cobaltates are famous examples, where actually by playing by the crystal field levels, or playing pressure, substitution, changing bond angles, one can have transitions from high spin to low spin situations or intermediate spin situations. Playing with this, just changing the crystal field level, the crystal field energy 10 dq. Okay. So one point I wanted to make in this situation, now I have 1 electron in the EG. Before I had a 5-fold degenerate system. If I have a spherical, or an atom in a spherical surrounding, if we have 5 different possibilities to put an electron. If I put 1 electron. And now, this is the orbital split up, but still I have now 2 possibilities to put this EG electron there. Either in the 3z squared minus r squared orbital, or in the x squared minus y squared. So there is still a degeneracy, and there is still a degree of freedom, and this is the degree of freedom now that I'm going to talk about. There's an orbital degree of freedom. And then this will be the rest of the lectures, but are the consequences of this in the strong coupling limit. Just to start off hand waving to give you some guidance, some idea why it is important, I just start with words and start with, instead of formulas. So spin versus orbital degrees of freedom, let's compare them. Well, as I will show, orbitals are, or I've already shown, are an excellent degree of freedom, and they can have impact on physical properties. Spins can order and disorder, and why not orbitals? They can also, in principle, order and disorder. But if they can disorder, they will contribute to thermodynamics, for instance. I will show you actually that also these orbitals determine, for a large part, magnetism, in that they determine which kind of magnetic structure, which type of magnetic ordering is formed. And moreover, the orbitals be strongly coupled to lattice distortions. This is because the orbitals, as I said yesterday, actually quadrupole moments of charge. If I change now the orbital occupation, I change the quadrupolar charge occupation. If I change some charge in real space, then of course the lattice will adjust to this reorganization of charge. And that's a fundamental reason why orbital degrees of freedom in general couple to the lattice, or rather strongly to the lattice, to the same quadrupolar deformations of the lattice that correspond to this quadrupolar distributions of the orbital charge. Okay, orbitals behave like electron spins, the spins of electrons, I should say, and let's now compare them very, very roughly, hand-wavingly. Okay, 90% right, 10% wrong. Similarities. They are both, well, local moment emerging from electron-electron interactions. Okay. And as I will show you, the angular momentum follows the SHU algebra. Yeah, for the, at least for the x squared minus y squared orbitals. Saying, in fact, that these orbital degrees of freedom are described by a two-component spinor, just like a spin 1/2. Yeah. So mathematically, they're just like a spin 1/2. They have a possibility of long-range order, and as I will show later today, spin and orbital interactions are both due to super exchange. Okay. Now let's do the differences. Again, very rough arguments, but just to get some idea. The coupling to the lattice of spins. Well, spins normally do not couple very strongly to the lattice. Why should they? How can spins couple to the lattice? Well, by a spin-orbit coupling. This couples the spin space to, say, real space, or crystal space. And if, as long as spin-orbit coupling is weak, which is true for the 3Ds, let's say, in general, much less so for the 4Ds and 5Ds, as I pointed out yesterday. But if spin-orbit coupling is weak, then the coupling to the lattice is not so big. And I said, I just made the argument that the coupling to the lattice for orbitals is rather strong because of this. Orbitals represent the real quadrupolar charges. This has a very general consequences for the symmetry of the Hamiltonian. So because the spins do not, or weakly couple to the lattice, and let's say for now, they do not couple to the lattice, then the symmetry of the Hamiltonians normally is very high. There is rotational invariance in my Hamiltonian. Why not? Because it cannot couple to real space, so there has to be internal rotational invariance. And this you have seen already in the Heisenberg model, where in fact the spin-spin interaction is such that it only depends on the relative orientation of spins. It is a dot product, so it does not depend on the total angle, the rotation of the spins, only on the relative angle of the spins. So I have a high symmetry of the Hamiltonian, whereas for orbitals I cannot make that argument, so I have a low symmetry of the Hamiltonian. So let's say here I can think about rotational symmetry of the Hamiltonian. The first approximation would be ridiculous to think about that if I talk about orbital Hamiltonians. You will see this. This has again a consequence for the excitations, because if I have rotational symmetry of a Hamiltonian, then if there's long-range order, I know that the excitations related to the breaking of that continuous symmetry are gapless. These are Goldstone modes. Right? So therefore, spins, as a Heisenberg model, has gapless modes. Your magnets, they go to zero, energy of the magnet goes to zero, as Q is going to zero. This is not true for orbital degrees of freedom. And then the last point, that will come in the next lecture, and maybe now also a little bit, the frustration of order. Frustration is of course now a big topic, and we have heard already yesterday about it, we'll hear much more about it. But spin Hamiltonians are frustrated, can be frustrated, and that mostly is the case if I consider for this triangular lattice. So geometrically frustrated situations. I'll show you that actually the situation is different, and for all the recursive frequencies, actually the order is almost always frustrated. Also, if I'm living on a bipartite cubic lattice, orbital interactions are such that the system is intrinsically frustrated. Okay. So now you could ask many questions, but let's not do that. Let's now go to a little bit in the mathematics, and then I hope that some of these things really will become clear. Orbital representation. So like I said, an SU2, let's look for an SU2 pseudo-spin representation for the EG orbital duplet. Okay, well, that's the same as spins. So I can consider also a spin 1/2, and then here is my spin operator, and that also Christian showed, where here I have a sum over repeated integers of the electron operators. I'm afraid to use this. Let's try. Okay. So this index alpha beta is up or down, and this is the spin 1/2 is therefore a 2-component spinner. Okay. There are of course the Pauli matrices. I've labeled them with sigma 1, sigma 2, and sigma 3, and not to label them with x, y, and z, because I have already used x, y, and z to talk about these orbitals. So I noticed myself that when I prepared the talk, I was very conscious in using 1, 2, and 3 here, and then later I switched to x, y, and z, of course. Okay, so I'm sorry if that's still in, but at least in the beginning, these Pauli matrices labeled by 1, 2, and 3. This is my spinor, and the identity matrix I can call sigma 0. Okay, that's all fine. And now, for instance, you can, by these definitions, you have S3, which you think about as Z normally, which is a half C dagger, or C up, C dagger up, number of up electrons minus the number of down. Okay, all fine. If I have the spinor, I can rotate this 2-component spinor, and the rotations of the spinor are generated by the 3 Pauli matrices. So how does the rotation work? Well, the rotation of the spinor by an angle phi around the axis j, where now j is 1, 2, or 3, avoiding to say x, y, or z, is the rotation operator rj is here, is e to the I phi sigma j, the Pauli matrix corresponds to this axis, phi over 2. This is all well-known stuff in textbooks. So you can also write this exponent as in form of cosine and sine. It's sigma 0 cosine phi over 2, identity matrix, plus I sigma j sine phi over 2. There's an I in there. So to give an example, if I have a spin up, which is, let's say, spinor 1, 0, and the spin down, spinor 0, 1, I can rotate by 2 pi around the 1 axis. 1, you can think about the x-axis. So what happens if you rotate a spin by 2 pi? So if you rotate spin up by 2 pi around the x-axis, well, you get the same spin, of course, but with a minus sign, because it's a spin. Right? This is the typical situation for spin. So rotation of, let's say, I call this R1, so rotation by 2 pi around the 1 axis gives me the same spin, but now with a minus sign. I have to rotate the spin 4 pi to get back to the original wave function. So this is known stuff that now I'll use to describe the x squared minus y squared and 3z squared minus r squared orbitals. So I can now introduce a pseudo spin called T, not S, which is the same definition But now that the beta and the alpha create and annihilate and create electrons in the x squared minus y squared or 3z squared minus r squared orbital, instead of creating spins ups and downs. Yeah, so I can say what I represented as 1, 0 now is x squared minus y squared. The 0, 1 in my previous slide is 3z squared minus r squared with the famous square root of 3. This is where the square root of 3 is important. Because I'm going to look at rotations. I'm going to rotate the spinor by an angle pi over 2 equals plus or minus 2 pi over 3. So on the unit circle, I'm either going this direction or I'm going that direction. Yeah. Around the 2 axis, which you can think about the y axis. But this y has nothing to do with this y there, so that's why I call it 2 axis. Okay, let's do that. Here's my rotation, R2. That's the way I have to do it, around the 2 axis. And if you just calculate this, I put in 2 pi over 3 for this angle phi over 2, you get this expression in terms of Pauli matrices, and this is the rotation matrix that you're dealing with. Okay, so now let's rotate the spinor. Rotate x squared minus y squared. So apply R2, this rotation operator around the 2 axis. So this operation on 1, 0, this is a matrix, or this is a multiplication, and I get this spinor here. And this thing actually I can write as minus 1/2 x squared minus y squared up there. So that's minus x squared plus y squared, minus or plus, depending if I do the rotation, say clockwise or anti-clockwise, minus or plus the 3z squared minus r squared, which, if I think I take the minus sign, I get y squared minus z squared. If I take the plus sign, I get z squared minus x squared. So what I've shown is that if you rotate your spinor, or if you have an x squared minus y squared orbital, and you rotate around this 2 axis by 2 pi over 3, pi over 2 pi over 3, you get the same orbital, but just with in another direction, with different coordinates system. So here I have x squared minus y squared, I rotate by 2 pi over 3, I get the orbital y squared minus z squared, and another 2 pi over 3, I get z squared minus r squared. And of course I can do the same thing actually for the 3z squared. If I do that, like this 2 pi over 3 rotation, first I get 3x squared minus r squared, and then I get 3y squared minus r squared. So it looks like this. So the 3z squared, actually you can check for yourself, if you have the 3z squared, and now you rotate by pi over 2, you get the x squared minus y squared. So 90-degree rotation gives me x squared minus y squared. If I have the 3z squared minus r squared rotated by 2 pi over 3, I get x squared, and another one, other rotation, I get the y squared. So pictures makes it easier. So here are my EG orbitals, and I rotate them by plus minus pi over 3. I start with x squared minus y squared, rotate around this axis, spinor axis. Here I get the y squared minus z squared. And you see that's the same orbital, but now in a different plane. And that rotation, again, same orbital, but in a different plane. 3z squared minus r squared, just cigar shape sticking out, rotated. Now it's along the x-axis, and if I rotate again, it's along the y-axis.
Should this red equation be phi equals plus minus 2 pi over 3?
No, it's phi over 2 plus minus pi over 3 for the spinors, for the orbitals. Yeah, but this factor of half is important. But it's related that if you have phi over 2 pi is a rotation of the spinor maps to itself. But that means that phi is 4 pi. So you make a 4 pi rotation of a spin to get back to its original position. Okay, more questions. So this is a little bit of playing around, but it's important for me later to use these tricks by rotation to get some simple Hamiltonians out of it. Okay,
So,
Yeah.
okay, we see that the orbital has fourfold symmetry, actually, but the angle is 2π/3 is because the 3 quantum number of the orbital make that rotation.
So let's okay. You're addressing exactly the point, which is say conceptually a bit different. So the
Can you repeat
rotation.
the question?
So okay, is the 2π/3 related to the fourfold symmetry of the orbit? And the answer is no. So that's why I introduced this 1, 2, and 3 axis, saying because these rotations are only 1, 2, and 3 axes, I have nothing to do with x, y, or z. And these are just rotations in orbital space, in this internal SU2 space. If I do a rotation in this SU2 space, with some angle along some axis, I get out different orbitals in real space. The symmetry of these orbitals, the underlying symmetry that for x squared minus y squared is fourfold degenerate, has nothing to do with that. These are just objects that I'm rotating, and it turns out that if I draw pictures of them, they look like this. But the axis of rotation, the angle of rotation, has nothing to do with the real space symmetry of those orbitals.
So where does the over 3 come?
Where does the 2π/3 come from? Good question. I don't know. I don't know. Maybe there's something deep. I don't know. Well, yeah, you would say well, I know that I have 3 axes, right? So if I want to change x from y and y from z, there's only one way to do it. That's cut the unit circle into 3, and that's 2π/3.
So it's the dimension.
Then that's the dimension, the 3D, right? Okay. Yeah, that's intuitively I would say that's correct. Okay, so I've rotated these wave functions, so to say, the spinors. But I can also rotate the spin operators, t. So if I rotate the spin operator here, as I was defined, now I have 2 rotations in there for the C and the C dagger. If I do this, for instance, along π/2 is equal to 2π/3, you can see that this T3 to Tz, for instance, goes to, well, just to evaluate this matrix product, and you see that you can easily derive it goes to minus T3 plus square root of 3, again, the square root of 3, T1 over 2. Yeah? If I rotate in the other direction, I get the same thing, but then with the minus sign there in front of the T1. So, conclusion, if I rotate by π/2 equal to plus minus 2π/3, the T3, which you can think of as Tz or Sz, goes to this guy. Again, it's on the unit circle. Okay. But yeah, I have a note here. So that works all very well for the EGs. How would you generalize this way of thinking to the T2Gs? And I got a little bit carried away. I don't think anybody really did this, but the way one should do it, I think, is the following. Well, in the T2G, I have 3 orbitals, which I can think of as 3 flavors, or 3 colors, if you want, 3 things, right? 3 possibilities. So, instead of an SU2 representation, I will take an SU3 representation. As you know, for instance, if you are dealing with quantum chromodynamics, you have 3 colors of the quarks, which is represented by SU3. Okay. So what does that mean? That I have a 3-component spinor. So XY is 1, 0, 0, XYZ is 0, 1, 0, and ZX is 0, 0, 1. And now again, I can write down my operators here, but I have to think about, well, which are the matrices that generate the rotations of SU3. Of SU2, the rotations are generated by the Pauli matrices. Of SU3, rotations are generated by the Gell-Mann matrices, which are 8. So and here, well, I didn't put the zeros in here not to clutter the picture, but these are the 8 Gell-Mann matrices. So these are the rotations corresponding to these spinors. These are the generators of rotations of these spinors. And actually, you could write probably if you're dealing with D2G systems, this would be the natural choice to write your operators and also to write your Hamiltonian in that manner. And you see actually that, of course, now 3 by 3 matrices, so my space is much bigger, but still I have 3, or I can look at this as 3 independent SU2 subgroups. For instance, lambda 1 looks like sigma 1, whole matrix. Lambda 2 looks like, here in the upper corner, like sigma 2, and actually this guy looks like sigma 3. So these 3 guys, they generate an SU2 group. Now the other guys here, lambda 4 and lambda 5, this also looks already like the sigma x and the sigma y, sigma 1 and sigma 2. But now I need a linear to close this. I need a linear combination of lambda 3 and actually of lambda 8 to get the corresponding sigma 3. And the same is true for lambda 6 and lambda 7. Again, they are closed by a linear combination of lambda 3 and lambda 8. So, yeah.
So, what is the meaning of let's say, doing this rectification, right? If there's no Hamiltonian. So, for example, I mean, why can't I take S equals to 1 to state equals to 3?
You're right. We need the Hamiltonian. Now we go up to the Hamiltonian. I mean, this is just exercise for the fun of exercising it with a. You're right.
No, but why is it 3? What's the fundamental difference?
Look, why? Okay, you say, okay. Now, there's no Hamiltonian there, so there's no reason, right? Because I'm just talking more general. I say, okay, now if it's a 3-component spinner, to rotate the 3-component spinner, I need 3 by 3 matrices. That's it, right? And these are the 8 matrices generating the rotations. I'm just using this mathematical fact. So you can also ask why the 8 Gell-Mann matrices and why not rotations of those. That's also possible. Or do you want to say there's not a unique choice? That's another way of saying there's not a unique choice of the generators of these rotations. That's also true. But if I talk about 3-component spinners, these guys generate rotations. That's my only observation. If this is useful or not depends on how I'm going to write my Hamiltonians.
What is the meaning of lambda vector?
So that's okay. Well, so this is it's 1 to 8. So there's a t vector here. There's a lambda vector here.
So at this point it's an 8-component vector.
Yeah.
Question?
Okay. Yes.
With the Pauli matrices, you rotated with sigma 2,
Yeah.
right? How would you know which width matrix to rotate here?
Good question. Okay. Let's. I got, like I said, this was my hobby. I did it just for fun, to generalize it. If anybody wants to write matrices and start doing rotations in this way, you're most welcome to. And this is probably a very nice way, the real story to it, to generate the Kugelkomsky Hamiltonians in the T2G sector, which I didn't do, but anybody's welcome to do it. It's, let's say, an open problem, and it's maybe could be a kind of nice way to obtain old results. Which is actually the reason why I introduced this rotation in the first place, which I want to get to now. Let's propose more questions a little bit later. So, to do this, I'm looking at orbital hopping. So, how does the hopping go from one orbital to the other orbital? For instance, from 3z squared to 3z squared along this z-axis. Now, you know how it is. I can call this hopping from orbital 2 to orbital 2 is equal to 1. They have a full overlap. However, this hopping from this orbital to that guy is 0 by symmetry. Remember, this has a plus and a minus lobe, so these lobes are plus, the other lobes are minus, so the overlap, this thing is just plus, with that guy, is 0. And actually, this situation is of course the same if I'm down there x squared minus y squared, up there 3z squared, and also if I have two x squared minus y squared orbitals, this should be 0. I'm sorry, this hopping should be 0.
Why?
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 It should be symmetry allowed.
Okay.
No?
Now there's a different level of answers. I think. So let's do the simplest answer. Yeah. The simplest answer is, well, if I look at real transition metal oxides, but I'm going to look to, there's no direct overlap of D and D. There's always an oxygen in between.
Then yes.
Okay. So if there's an oxygen in between, then this is absolutely true. Yeah. Another way of saying this is in terms of the type binding description is that you have this dd sigma, dd pi, and dd delta, if you remember the book of Harrison. I'm just saying dd delta is 0. That's another way of saying it. The same thing. But let's for the moment say, let's imagine the hopping here is via the oxygen, which I just took out. But then this is definitely not the case. That will be 0 here, which is definitely the case. Yeah. Okay, so this is easy now. Now hopping along the z-axis is a 1 here, down there, nothing else. What's now the hopping for these orbitals if I don't put them along the z-axis but along the x-axis? Well, I rotate just these hopping matrices. I can do that easily by the rotations I've shown. I get the rotation that along the tx, along the x-axis, is 3, 1, get the square root of 3 there. The hopping along the y-axis, same thing, but then at the minus sign in front of the square root of 3. What does this mean in terms of picture? I have this hopping that's 1 between those two orbitals. I rotate by 2 pi over 3, both orbitals. And now the hopping I consider is between these two guys, while the hopping between these two guys is of course exactly the same by rotating this whole thing and putting them along the x-axis. Just rotating in my mind along the x-axis. Yeah? So I can take my original orbitals, rotate these guys, I rotate these guys, actually I generate the hopping of these orbitals along another axis. Okay, so that's nice. How does this influence superexchange? Let's do the same thing. The superexchange is the Hubble model, right? I consider two sides, I and j, with two Eg orbitals, each two Eg orbitals, and one spinless fermion. Let's forget about the spin of this guy. So the other side I have the two orbitals, side j have the two orbitals, and only I can hop from 3z squared to 3z squared. I imagine these orbitals to be along the z-axis. So I can also say I have a tz spinor that's minus 1/2 if the electron is in the x squared minus y squared orbital, and it's plus 1/2 if it's in the 3z squared minus r squared orbital. Okay. Two electrons on the same side, if they hop, then they pay energy U. If they're on the same side, they by definition have to be in different orbitals. These are spinless fermions. I cannot have two spinless fermions in the same orbit, by definition. So the energy gain is minus t squared over U, and this is only possible if there's, say, one electron here and the other one down there, or one electron up here and another one down there. So in terms of this Tz, if this Tzi is in half and Tzj, so now the Z has to be a 3. So this is where I switched it from 3 to Z. Tzj is minus 1/2 or vice versa. So writing this in terms of a Hamiltonian is, okay, here I multiply these two factors. Right? Both have to be 1. So minus t squared over U, this first factor, so a half plus SZI, which means this is 1 if SZ is a half, if it's 0 if SZ is minus 1/2, times 1/2 minus SZJ, which fulfills this condition, plus the other guy. multiplying this out very simply gives me that the Hamiltonian, the super exchange Hamiltonian, along for orbitals along the z-axis is j over half Szi minus a constant. So I have Ising type exchange Hamiltonian. Like I said, not Heisenberg at all, no rotation symmetry, the opposite. Okay, this is along the z-axis. How can I generate this stuff along the x-axis and the y-axis? Because I have three directions. If I look at these d2g orbitals, at least in a cube, on a cubic system. Now, I know I have my recipe to do so. I have these rotations by 2 pi over 3. And I know that my orbitals rotate, or my operators rotate in this manner. Which means that along the x-axis, along the z-axis, I left out the constants here. I have tz, tz, or tz, tz. Along the y-axis, I get this linear combination of tz and tx multiplied, and along the x-axis, I get the same combination, but now with the minus sign. These are my these are my Hamiltonians now that I'm looking at. Okay, I can say, well, this is now the equivalent of the Heisenberg Hamiltonian, but now only for orbital degrees of freedom. Yeah. Can I rewrite this? Well, the way I can rewrite this in a kind of compact way is this model is called a 120-degree orbital model on a cubic lattice, and I can write it the following: the sum over size I, t gamma I plus e gamma, where this gamma is 1, 2, 3, or x, y, z. This t gamma, is the linear combination of tz and tx with an angle, mixing angle theta gamma, but the theta gamma is 0, 2 pi over 3, 4 pi over 3. Just rewriting this thing in that way. And this index gamma now, I did carefully, goes over 1, 2, 3, and the vector connecting neighbors, so I and I plus e gamma, this vector e connecting neighbors, if I'm on a cubic lattice, these are just the cubic vectors. So the e gamma is, say, ex, ey, and e. So this now concludes the EG model. Okay. In the picture, the 120-degree contrast model, so without spins, just orbitals. Just in the picture, I have this free axis. Along one axis, the interaction is, well, let's take the axis first. Along this axis, the EZ axis, the interaction is tz, tz. Let me see if I can get that out of it. Well, this is a different definition. Along the other direction, there is this interaction is tx plus, or sorry, tz plus square root of 3 tx, and the other one is negative. So you see, the important thing is, compared to the Hubbard model for S electrons, say, that now the interaction is different along the different directions in real space. Where for the Heisenberg model, on each bond, the Hamiltonian is Si dot Sj. For orbital models, for Kugelkomsky models, which we'll get to next, the situation is different. Along each bond, the interaction takes a different form. Okay, that's what I want to say today.
I didn't get why do you say that dV delta is 0? Like it just without the oxygen.
Right. I assume it's 0.
Okay. You just,
That's it.
okay.
I should have said I assume it's 0, and then I'm in business. In general, it's not. And also, actually, I, for instance, considered only spinless fermions here, where in real life these fermions have a spin. And also, if they have a spin, then there's the Hund's rule interaction if they are on the same side, which is another complication which I'll talk about tomorrow.
So I couldn't get how frustrated this, for example, this case.
Perfect question. This is how frustrated it is.
Yeah.
Yeah? So along, let's say, if I take the essence of this, along one direction I have TZ. So the spins want to point along the Z axis. Along the X direction, I have the interaction is TX, spin wants to point around the X axis. On this third, the interaction is like, I can think about TY, or let's think about this situation. This is quite similar to this, if I have this situation. And the question, of course, is where in the middle I want to put my spin. So there are three equally good or equally bad possibilities now for the central spin. And this why the interactions are intrinsically frustrating. Thanks for that question.
Now, how do possible ordered phases look like?
Okay. Another few slides, but so actually in this case, one can show that if you look at this model classically, then the order parameter is infinitely degenerate. So the answer is the orbital is always staggered, but in which direction the orbital order parameter is pointing, along the x-axis or along the z-axis, energy, classical energy does not depend on that. It's rotational invariant. So which means that you get back some rotational invariance in this model effectively for the ground state manifold. If you have this, then the ground state manifold is degenerate, but the excited states are not. Do not have the symmetry, because the Hamiltonian does not have the symmetry. If this is the case, you can get order by disorder. So in this model, actually, you get order by disorder. For the quantum model, I don't think there's any proof. I don't know, maybe Daniel knows better, but for the classical model, I know there is a proof that there is order by disorder. So it's a very non-straightforward.
You will discuss this.
Yeah.
If I follow Slater coaster notation, will I get the same hopping term that you get through pseudo spin?
If you do what?
The Slater coaster.
Yeah, you get the same. So if you do the Slater coaster, forget about and you put an oxygen in between, so you have the T, PD, and so on, then you get this. And 90 or 180 degree bonds. And if those bonds are not 180 degrees, then you get small order terms with it. Which is important because, as I said, this model has really difficulties to order. So all kind of next small corrections will kick in and actually determine the order. Small perturbations become very relevant.
Following another question. So you have not shown the AF electron things, but can you comment on it? Like what kind of symmetry or degeneracy you can expect there?
Yeah. So F, I would say, in principle, you can do the same thing for F electrons. But for 4F, I wouldn't do so much efforts because these guys are so localized. There's not the direct overlap between F4F and 4F that determines something like superconductivity. It's much more what Matthias has shown. You're dealing with quantum models now, you have or quantum lattice models, and plus the scope of degrees of freedom. So that's a kind of different problem. Also.
No, I'll just start with the bare.
For instance, 5Fs, you could say, well, why not 5F?
Is there any reference that you can recommend?
Let's say like that. I mean, I don't know of anything being done on this kind of general level for the 5Fs or for the 4Fs. You can do the same thing. And but now one complication you will for certain you have to take into account the spin orbital, which kind of destroys the nice symmetries that I've shown here. So you have to do spin orbital, but then in principle you can do the same thing. You can again get out doublets and write down some algebra for these doublets and look at the symmetries of all this and generate a super. You can do the same thing.
You mentioned it was spinless fermions, right? And there was a U somewhere in T square over U. What is that U referring to then?
Two spinless fermions are on the same side, which means they have to be on the same. They have to be in different orbitals.
So it's the interorbital Coulomb interaction of spin.
Yeah, because that's then the only one I have. That's
Right.
my way of kicking out U prime and J.
And so if I were to introduce spin, that would change altogether, or?
Yeah. That would change, that's the next step. But actually, because I know I did this a little bit of work on all this symmetry stuff, it only takes 1 or 2 slides to get the if I include spin, these are the Kugelkomsky Hamiltonians. Sorry, Daniel, I'm so often saying Komsky, and I know that's the person in the audience to say always is the name of them. But this is how these Hamiltonians are called. So you can derive them very simply or very straightforwardly by all these rotations, and then including the spin, where you have more possibility.